Let's now take a look at the different techniques of integrating a function numerically. In your math classes, you've learned that in order to integrate a function, you first divide that function into intervals, as shown. The function at each interval is represented by a rectangle of a specific height and width. Integration is simply taking the area under the curve, which in this case is the sum of the area of the rectangles. So if the first rectangle has an area A1, the second A2, A3, A4, A5, and A6 for the third, fourth, and fifth rectangles, the integral from A to B is just the sum of the areas of these rectangles. You can imagine that if we decrease the width of each rectangle, or the size of the intervals, the number of rectangle increases, but it approximates the function much better. Mathematically, we say that if we let the interval size approach 0, then the error of the integrating function is also reduced considerably. The Newton-Cotes formula are the most common numerical integration schemes. They are based on the strategy of replacing a complicated function or tabulated data with an approximating function that is easy to integrate. As shown, f of x is replaced by a function f sub n of x, where f sub n of x is an nth order polynomial. For example, a first order polynomial is a straight line. A second order polynomial is a parabola. The integral can also be approximated using a series of polynomials applied piecewise to the function or data over segments of constant length. The trapezoidal rule is the first of the Newton-Cotes closed integration formulas. It corresponds to the case where the polynomial is of the first order, or linear. Recall that a straight line can be represented as shown. The area under a straight line is the estimated integral of the function f of x between the limits a and b. As you can see, this integral, or this area, has a very large error because there is an area that is not accounted for. The area under a straight line is an estimate of the integral of f of x between the limits of a and b. If we replace f of x in the integral with f sub 1 of x, we then get this expression. Geometrically, the trapezoidal rule is equivalent to approximating the area of the trapezoid under the straight line connecting f of a and f of b. An estimate for the local truncation error of a single application of the trapezoidal rule is the following expression, where eta lies somewhere in the interval from a to b. This equation indicates that if the function being integrated is linear, the trapezoidal rule is exact. This assumes that for small h, the second derivative term is approximately constant. Let's consider this example. Use trapezoidal rule to numerically integrate f of x equals 400x to the fifth minus 900x to the fourth plus 675x cubed minus 200x squared plus 25x plus 0.2 from a equals 0 to b equals 0.8. The exact value of the integral can be determined analytically to be 1.640533. So if we use only a single interval from 0 to 8, we begin with the function values at f of 0 and f of 0 plus 8. These values are equal to 0.2 and 0.232 respectively. If we substitute these values into the equation for the trapezoidal rule, we have I equals 0.8 times 0.2 plus 0.232 divided by 2 equals 0.1728. Comparing it with 1.640533, the error is approximately 89.5%. This is an extremely large error, as you can see, because the area that was computed is only this value, and this area has not been taken into account in the integration. So how do we improve the accuracy of this computation? One way to improve the accuracy of the trapezoidal rule is to divide the integration interval from a to b into a number of segments and apply the method to each segment. Thus, in this first example, it was divided into 2 segments, and then you apply trapezoidal rule to this segment, and then a trapezoidal rule to this segment, so you have 2 integrands. In this second case, you have 1, 2, 3 intervals, and you have 1, 2, 3 results for the integration, and the resulting integral is just the sum of these 3. If you apply 4 intervals, 1, 2, 3, 4, then you get I equals I1 plus I2 plus I3 plus I4. Then you can see that this result is much better compared to this result or this result. If you increase the number of intervals further, then we would expect that the error becomes smaller and smaller, and that our integration becomes more accurate. The areas of the individual segments have been added to yield the integral for the entire interval. These resulting equations are called multiple application or composite integration formulas. There are n plus 1 equally spaced base points, and consequently there are n segments of equal width. If a and b are designated as x sub 1 and x sub n plus 1 respectively, the total integral can be represented as, so I equals x sub 1 to x sub 2 plus x sub 2 to x sub 3 plus the inner terms up to the integral from x sub n to x sub n plus 1. Substituting the trapezoidal rule for each integral yields, so this is for the first term, this is for the second term, and this is for the nth term. Grouping similar terms, we'll end up with this expression. How do we do that? Notice that this term and this term are the same. Also, there's a term here, f of x3 divided by 2, and there's another term here, which is f of x3 divided by 2, and so on and so forth. Finally, towards the end, you have a term f of x sub n divided by 2, and another term here, f of x sub n divided by 2, which you also combine. These terms that I've shown with colors correspond to this term. What about the h1, h2, h3 up to h sub n? Again, we assume equal intervals, which means that h1 is equal to h2 is equal to h3 equal to h sub n, and they're all equal to h. That's how this equation was derived. If we replace h in terms of a and b, we get the following expression. So this should be b minus a. Let's consider the same example. In this case, we divide the function into 2 intervals, n equals 2. That means that if this is your function, this is x equals 0, this is x equals 0.8. Dividing it by 2 intervals means we have 0.4 here. So this is your first interval and this is your second interval. This is what n equals 2 means. H equals 0.4 means that each interval has a width of 0.4. So the value of the function at x equals 0 is equal to 0.2. the value of the function at x equals 0.4 is equal to 2.456, and the value of the function at x equals 0.8 is 0.232. Thus, if we use the Newton-Cotes formula derived earlier, we arrive with 0.8 times 0.2 plus 2 times 2.456 plus 0.232 all over 4. This gives us an integral result of 1.0688. And compare that with the analytical value of 1.640533, we get 0.57173, or an error of 35%. You can imagine again that if you improve or increase the interval sizes, you improve the integration, the value of the integral, and also decrease the error. So here are the results for the use of the trapezoidal rule for various values of h. Here we use the value of h equals 0.4, which results to two intervals, 1 and 2. If we use h equals 0.2, we have 4 intervals, and each interval is equal to 0.2. If we use 0.8, this is not 0.08, but instead 0.8, then we have 8 intervals. For h equals 0.4, the integral is 1.0688. For h equals 0.2, the integral is equal to 1.4848. And for h equals 0.8, the integral is equal to 1.615. And this is already quite near to the analytical value of 1.6. Another way to obtain a more accurate estimate of an integral is to use higher order polynomial to connect the points. The formulas that result from taking the integrals from these polynomials are called Simpson's rules. To be able to use the Simpson's rules, we use the Lagrange interpolating polynomials. The Lagrange interpolating polynomial is simply a reformulation of the Newton polynomial that avoids the computation of divided differences. It can be represented concisely as shown. While it can look mathematically daunting, it's actually quite simple. The function f in the integral is replaced by the function f sub n of x, which is equal to the sum from I equals 0 to n of L sub I of x times f of x sub I, where L sub I of x is your Lagrange interpolating polynomial, which is equal to the product from j equals 0 to n of x minus x sub j divided by x sub I minus x sub j. Note that j must not be equal to I. For example, in the linear version where n equals 1, we solve for f of 1 of x. This will be equal to sum from I equals 0 to 1 of Li of x f of xi. This is equal to L naught of x f of x naught plus L1 of x f of x1. So if I is equal to 0, then this equation will have x minus x naught divided by x naught minus x naught. But according to this should not be allowed, so we ignore that. Then we go to the next term, which is x minus x1 over x naught minus x1. And that's what we have here. Now for I equals 1, we have x minus x naught over x1 minus x naught, which is what we have here, multiplied by x minus x1 over x1 minus x1, but this is not allowed, so we remove that term. The second order term needs a little bit of work. So f of 2 of x is equal to L naught of x, f of x naught plus L1 of x, f of x1 plus L2 of x, f of x2. L naught of x is then equal to, so I in this case is 0, and here you have 2. So you expect to have only two terms. So the first term is x minus x naught over x naught minus x naught, but this term is not allowed according to the rules, so we delete that. The next term is x minus x1 over x naught minus x1. Then we multiply that by x minus x2 over x naught minus x2, which is the term that you have here. Now for I equals 1, we have x minus x naught, where j equals 0, divided by I equals 1, so x1 minus x naught. Now j must not be equal to I, so j, we don't need the x1s here for j, so we go immediately to j equals 2. So this is multiplied by x minus x2 over x1 minus x2 times f of x1, okay, which is the term that we have here. And then for the third term, where I equals 2, okay, we have x minus x naught over x2 minus x naught multiplied by x minus x1 over x2 minus x1. And since j must not be equal to I, then we don't need to compute for x, third term involving x2, x sub I equals 2 and x sub j equals 2. We're left with this expression times f of x2, of course. Okay, so we've derived this expression. Simpson's 1/3 rule results when a second order interpolating polynomial is substituted into the general expression for the integral. If a and b are designated as x0 and x2, and f2x is represented by a second order Lagrange polynomial, the integral becomes as shown. This equation is known as Simpson's 1/3 rule. It is the second Newton-Cotes closed integration formula. After integration and algebraic manipulation, the following formula results. If we replace h by b minus a all over 2, we have this expression. The error term is computed as shown and is in the order of the fifth power of h. Just as with the trapezoidal rule, Simpson's rule can be improved by dividing the integration interval into a number of segments of equal width. The total integral can be represented as shown. So this is your first interval, this is your second interval, and so on and so forth, and this is your last interval. Substituting Simpson's 1/3 rule for the individual integrals yields the following expression. This was obtained from this term, this was obtained from this term, and this was obtained from this term, where h is equal to b minus a all over n. By combining same terms, we end up with the following expression as shown. These same terms are as shown. So f of x2, f of x2, we have f of x4 there, and another f of x4 in the third term, and so on and so forth. And this combines with the same expression in the previous term. So we end up with this expression. I equals b minus a times this whole expression for f. If we use the same example, let's divide the function into n equals 4 interval. This means that h equals 0.2. So we have x equals 0, x equals 0.2, x equals 0.4, x equals 0.6 and x equals 0.8. At these values of x, we have f at x equals 0 equals 0.2, f at x equals 0.2 equals 1.288, f at 0.4 equals 2.456, f at 0.6 equals 3.464, f at 0.8 equals 0.232. Notice that in this expression, the first term is f of x naught and the last term is f of xn. In the second term, all the odd terms are combined and multiplied by 4. The third term, all the even terms, are added and multiplied by 2. In this example, we have 5 terms. So the first term is f of 0, and the last term is f of 0.8. These are our odd terms. So we add them up and multiply by 4, as shown. This is the only even term, so we multiply that by 2. Then using Simpson's 1/3 rule, we obtain the value of the integral to be 1.623467, which is an error of 1.04%. The small error is not just due to the interval size, but it's because we have used a second-order polynomial in the form of Lagrange interpolating polynomial. Simpson's 3/8 rule results when a third-order interpolating polynomial is substituted into the general form of the integral. If a and b are designated as x1 and x4 and f of 3 of x is represented by a second-order Lagrange polynomial, the integration and a little algebra yields the second expression, where for this case, h is equal to b minus a divided by 3. This equation is known as the Simpson's 3/8 rule. It is the third Newton-Cotes closed integration formula that we will learn. It can also be expressed as shown, along with the error term proportional to the fifth power of h. Simpson's 3/8 rule can be improved by dividing the integration interval into a number of segments of equal widths. Substituting Simpson's 3/8 rule for the individual integral yields the following equation, with h equals b minus a over n. Combining similar terms, we obtain the following final expression for the integral. For cases where the data has unequally sized segments, we apply either or both the trapezoidal or Simpson's rule to each segment. Using entirely the trapezoidal rule, the sum results to the following expression. You may combine any order of the Newton-Cotes equation, as you can see here. However, you can also see that the process is very tedious because you have to manually select which is more appropriate over certain intervals. Now that we've taken a look at the various methods of numerical integration and also at the sneak peek of the implementation in MATLAB and Python, you can begin solving machine problem 3. Your task is to improve the accuracy by extending the integration to n intervals. In the next lesson, we'll explore matrices, matrix operations, and their applications in solving systems of equations. See you in the next video!